Formally, we define Poisson process as follows. A stochastic process n of t greater than or equal to 0 is said to be a Poisson process with the intensity or rate lambda greater than 0 if the following conditions are satisfied. First condition, it starts from 0, that is n of 0 is equal to 0. Second condition, the increments are stationary and independent. Stationarity means that for time points s and t, s greater than t, the probability distribution of any increment n of s minus n of t depends only on the length s minus t of the time interval, and that the increments on equally long time intervals are identically distributed. Independent increments means that for any non overlapping intervals t comma s and u comma v, the random variables n of s minus n of t and n of v minus n of u are independent. For t greater than 0, n of t has a Poisson distributed random variable with the parameter lambda t. And the difference of the random variables defined over non overlapping intervals are independent. Lambda t is the cumulative rate till time t. The xi's are independent and identically distributed random variables with some distribution function g independent of the Poisson process n of t, t greater than or equal to 0. It is Markov in nature because the two queues act independently and are themselves a moment queuing system which satisfies the Markov property. Assuming that each queue behaves as the moment queue. The details of the proof can be found in the reference books, because Qij's are obtained by differentiating the Pij's. For every t greater than 0, n of t has a Poisson distribution with the parameter lambda t. Like that you can go for many more increments also. For illustration I have made it with the 2 increments. That means the occurrence of arrival during these non overlapping intervals are independent, and the stationary means it is a time invariant, only the length matters, not the actual time. Third one, for every t, n of t has a Poisson distribution with the parameter lambda t. So, the Poisson logic is coming into the fourth condition only. The first condition is start at 0, increments are stationary and increments are independent. The third condition, for fixed t, n of t is a Poisson distribution random variable with the parameter lambda t. Therefore, this stochastic process is called a Poisson process. Now, we can relate the way we have done the derivation. We have taken care of these 3 assumptions starting at time 0, 0, increments are stationary, that we have taken, and increments are independent, that is non overlapping intervals are independent. Then when we have derived, we are getting the distribution of the random variable n of t is a Poisson distributed random variable. Therefore, this is a Poisson process. The another way of defining the Poisson process, we can start with the birth-death process. You know that birth-death process is a special case of a continuous time Markov chain. Also, it is a special case of a special case of a Markov process also. So, you can think of a stochastic process then the special case is a Markov process, then the special case is a continuous time Markov chain, then you have a special case that is a birth death process. So, you can define the Poisson process from the birth death process also. A birth death process n of t is said to be a Poisson process with the intensity or rate lambda if birth rates are constant for all I and the death rates are 0. You start from the birth death process with all the birth rates are same, that means it is a special case of pure birth process in which birth rates are constant for all the states and the death rates are 0. Then also you will get the Poisson process. Here I am giving us a sample path for the Poisson process. So, this is created using the MATLAB, write the simple code of Poisson process, then you develop the sample path. That means at time 0 the system at 0, at some time one arrival takes place, therefore, the system land up 1, therefore, the y axis is nothing but the n of t. So, at this time one arrival takes place, therefore, the number of customers in the system, number of arrivals till this time, that is 1. So, it is a right continuous function, the value at that point and the right limit is same as, both are same, which is different from the left limit of the arrival epoch, arrival time of epoch. So, the system was in the state 1 till the next arrival takes place. So, suppose the arrival takes place here, then the n of t value is 2 at this time point in which the arrival epoch and the right limit and so on. So, this is the way, therefore, the system at any time it will be the same value or it will be incremented by only 1 unit. The Poisson process sample path will be with the 1 unit step increment at any time. There is no way the 2 steps the system can move forward at even in a very small interval of time, the system will move into the only 1 step, that you can visualize here. Therefore, you can go back to the assumptions which we have started with the derivation, n of 0 is equal to 0. In a very small interval of time, at most 1 event can take place, and the difference of the random variables defined over non-overlapping intervals are independent, and increments are also stationary. So, those things you cannot able to visualize in the sample path. So, this is just one sample path over the time and n of t. The second one, inter-arrival times are independent, as well as we can conclude the inter-arrival times are exponentially distributed also. The inter-arrival times are independent and each follow exponential distribution with the parameter lambda. What is the meaning of inter-arrival times? At time 0, the system is in the state 0. First arrival occurs at this time point, second arrival occurs this time point, and the fourth, third, fourth and so on. The inter-arrival time means what is the time taken for the first arrival, then what is the interval of time taken for the first arrival to the second arrival and second to the third and so on. So, that is the inter-arrival time. So, whenever you have a Poisson process, that means the arrival of event occur over the time that follows a Poisson process, then this inter-arrival time, suppose I make it as a random variable capital T, and those random variables going to follow exponential distribution with the same parameter lambda, and all the inter-arrival times also independent. That means these are all identically distributed random variable. I can go for different random variable label also, x1, x2, x3, x4 and so on. So, all those random variables are IID random variables and each follows exponential distribution with the parameter lambda. So, this can be proved easily. Let me start giving the proof for the first arrival time, that means the first one from 0 to the first arrival. Like that you can go for the other arrivals also using the other properties, or you can use the multidimensional random variable distribution concept and use the function of random variable, and you can get the distribution also. But here I am finding the distribution for the first arrival. So, let t denote the time of first arrival. My interest is to find out what is the distribution of capital T. I know that this is going to be a continuous random variable because it is a time. So, any time the first arrival can occur. So, to find, since it is a continuous random variable, I can find out the CDF of the random variable or complement CDF. So, here I am finding first the complement CDF. Using that I am going to find out the distribution. Let me start with the probability that the first arrival is going to take place after time t. What is the meaning of that? The first arrival is going to occur after time small t. That means till time t there is no arrival. So, both the events are equivalent events. The probability of t greater than small t, that is same as the probability of n of t is equal to 0. That means no event takes place till time t, because the n of t denotes the number of arrival of customers during the interval 0 to small t, both are closed, 0 to 1, 0 to t. Therefore, n of t equal to 0, that means till time t nobody turned up, that is equivalent of the first arrival is going to take place after t. I don't know what is I don't know the distribution of capital T, but I know what is the probability of n of t equal to 0. Therefore, I am writing this relation. So, once I substitute the probability mass at 0 for the random variable n of t, just now we have proved that n of t for fixed t is a Poisson distribution random variable with a parameter lambda times t. Therefore, I know what is the probability mass at 0. So, substitute the probability mass function with the 0. I will get e power minus lambda t, that is the complement CDF of the random variable capital T. Once I know the complement CDF, I can find out the CDF. From the CDF, I can compare the CDF of some standard continuous random variable. I can conclude this is nothing but exponential distribution with the parameter lambda, because this is a complement CDF at time t. Therefore, it is a lambda times t. So, I conclude the distribution of a capital T is exponential distribution with the parameter lambda. That means, the first time of arrival this random variable, that is a continuous random variable, and the continuous random variable follows exponential distribution with the parameter lambda. Since I know the increments are independent, increments are stationary and so on, I can use a similar logic for inter-arrival time of this time also, then that is also going to follow exponential distribution. Since the increments are independent, so this is the first time and this is second time, therefore, the inter-arrival time is also going to be independent. That means, whenever you have a Poisson process, that means the arrival occurs over the time in a very small interval, maximum one arrival takes place, and the probability of one arrival in that small interval is lambda times delta t. From that you will get the lambda. So, you can conclude that is a Poisson distribution, Poisson process. So, once the arrival follows a Poisson process, the inter-arrival times are exponential and independent. So, from the Poisson process one can get the inter-arrival times are exponential distribution and independent. The converse also true, that means if some arrival follows with the inter-arrival times exponential and exponential distribution and all the inter-arrival times are independent, then you can conclude the arrival process is going to form a Poisson process. That means arrival process, Poisson process implies the inter-arrival times are exponentially distributed and are independent. Similarly, inter-arrival times are independent as well as exponentially distributed with the parameter lambda, then the arrival process is a Poisson process with the parameter lambda.